Okay, so CasimirSim, a tool to compute Casimir Polder forces for non-trivial 3D geometries. Okay, I think everybody in this room knows what the Casimir effect is, right? You have two, for example, metallic plates and you introduce boundary conditions on the vacuum fluctuations, and this results in the force. This was first calculated by Henry Casimir in 1948, and it's pretty much the way he derived it. It's a retarded van der Waals type of force. This force has a dependence of 1 over distance to the fourth. So it becomes interesting if you go, for example, in sub-micron domains. So from 5 micrometers, for example, down to 10 nanometers, this force becomes really interesting. If you go below, you're basically in the van der Waals force regime, but between 10 nanometers and a few micrometers, that's where the Casimir effect is really working very well. And you know, when I first heard about this effect, that it's really cool, 2 plates and so on, but my problem with this Casimir effect was that if I want to build machines, if I want to think about how can I use this for propulsion, how can I use this for high-frequency gravitational wave detections, I have to think about, you know, how to build a machine using these forces, okay? And all these equations that are around are, for example, plate to plate. Then you will see, for example, plate to sphere is possible. And the latest, I think, news on this topic is that now you can analytically calculate plate versus cylinder. That's great, but that somehow limits our imagination. Yeah. So here you see, by the way, this is a plot from a paper from Science 2001. Where Federico Carpasso's group at Bell Labs, is now at Harvard, they basically published the first paper, application of the Casimir effect, activation of a MEMS device using the Casimir effect. Yeah? So this was the first publication, utilization of Casimir effect, 2001, and I believe we are going, you know, further down and down from MEMS machines to sub-micron scale machines, NEMS machines, that's how they call it. And in this NEMS world, the Casimir effect could be really used for applications. Yeah? And who knows, maybe nano robots can be used also for propulsion, energy production, whatever. But yeah, here's again, you know, if you want, for example, to calculate really to very good precision the force between these 2 plates, and you want to include, for example, the effects of that you have air instead of vacuum, whatever, you can do this for this plate-to-plate configuration using the Lifshitz formula. Okay? For those who like Mathematica, this is a very nice application. Okay? But for example, if you had studied with the Lifshitz, Landau-Lifshitz, a series of books on theoretical physics, the Lifshitz equation is one of the only ones where they write specifically that this is not specifically derived in the book, okay? So you can just imagine how complicated this is. Nobody is even daring to try to put the Lifshitz formula to other type of geometries, yeah? Highly complicated. So I said, well, I think there is a real need of coming up with a numerical tool to compute Casimir forces for really MEMS type geometries, because if you look at typical MEMS and sub-micron machines, which are, you know, for example, at Sandia, they're very, very, very good at doing this stuff. We are already approaching these regimes, and this doesn't look like plate to plate, assuming you have infinite long plates and these kind of things. These are real devices, okay? So that was the idea, and so I sat down a couple of years ago and started to develop this finite element software to compute Casimir forces for any type of arbitrary geometries. And I did this because something in my mind told me it's really interesting plate to plate. So I can visualize this if I have a plate to plate geometry that the vacuum, you know, density inside, the energy density is less than outside, and so it's pushing on the plates. What's happening if you have groove-like structures instead of plate-to-plate geometries? And would this create, for example, a pressure gradient in vacuum that you could use for propulsion? This was somehow an idea in my mind. And of course, there's no way how to calculate this analytically. So I came up with this software to calculate it. Unfortunately, the news is that there is no net force on the system. It's introducing a torque. But nevertheless, this was my starting point in how to really get into these Casimir applications. I'm sure we can, if you start using this software, we can have a whole session next year just looking at applications. What can we do with the Casimir? And well, how does it work, this finite element software? Well, like all this finite element stuff, you subdivide your objects into grid domains, and we're just summing up, similar to what Casimir originally proposed. He said the Casimir effect is a retardation of the van der Waals forces, so we calculate the interaction potentials between one grid cell with all the other grid cells.
Well, you got a symbol in there I'm not understanding. Alpha M, and then there's something in between next to the alpha E. What is that?
Here.
No. It was in your previous slide too. What is that?
Oh.
Is that a less than, greater than, or an equal? Or is it a symbolic error?
Okay, that's a mistake. The thing is that this is the electrical polarizability. Exactly, it's the magnetic polarizability is much less than electrical polarizability.
Okay, because you had a condition on your previous slide about what A over R is it much less than 1?
Yeah, much less.
So that was what that symbol.
Yeah, sorry.
Microsoft probably screwed it up.
Yeah, but
access to printers attend to miss these things. It's not there.
okay. So the thing is that usually you can neglect the magnetic contribution. Some people claim that this leads to repulsive Casimir forces, but it can be included in the software. Nevertheless, there are no real materials up to now that make this possible. Okay, so this is this typical finite element scheme, and what you can see, we tried of course to test this simulation software against the non-analytical solutions. We tested it against plate to plate, plate to sphere, wherever we had analytical solutions. It turns out that, for example, this is basically the red line is our simulation. You see that, for example, for small distances, so if we're really sub-micron, that we're really converge very good with the analytical solutions. And we believe that our solution here is more correct than an analytical solution because we put here in real geometries versus the analytical solutions assume infinite long cylinders, infinite long plates, and so on. So that's the real correction factor. The software can give you the real, basically, Casimir force depending on materials, penetration depths in the materials, and so on. You can calculate it for gold. You can use silicon if you're in a MEMS world, and so on. So that can all be implemented basically in the software. I started off with simple rectangular meshes, and there are more than 7 objects that you can combine in your simulation domain to calculate these Casimir forces. You can calculate, how the Casimir force basically acts between the objects with respect to another reference, whatever. Yeah? You can implement whatever you like. This is our latest basically version. We implemented, mesh generators where you can very effectively also, for example, compute more or less large-scale objects. So, for example, if your object is a couple of micrometers in diameter, but you're looking at very small gaps between the objects, a lot of nanometers, for instance, where the forces are very, very high. And so you can use this tetragonal meshing and adaptive grid generation to really compute the occurrences where you need them. And that's what you can do. You can do triangles, you can do rings, you can do spheres, cylinders, whatever. You can put all this in your simulation domain. You can basically combine them. You can cut out. You can make basically any kind of thing. For instance, this is just an impression of what you can do, and what you can simulate. And this is then going to the meshing generators. The mesh generator is open source, so this is all freeware basically to use. This comes all in with our package. You can use this with Linux, Unix, or in a Windows environment. We supply actually both versions. And this is what you can do from the plotting. We are simulating here basically a nanomotor, a nanogear that we can activate with the Casimir effect. And that's actually what we then developed basically as the first application out of this simulation software. We implemented another feature because the Casimir effect unfortunately is always attractive. And it depends pretty much, it's material dependent and it depends on the distance. But what if we alter the material properties? I think Fabrizio Pinto already told you a little bit about this in his presentation a couple of days ago. Well, my proposal for that is the following. If you take, for example, let's say a barium titanate crystal, the Casimir effect basically has a linear dependence on the polarizability, so basically also on the relative dielectric constant. And these crystals are known to change the relative dielectric constant over a very short temperature range, very quickly. So I can use this, if I implement this into my Casimir effect, I can create forces where I can vary the magnitude of the force, by my own means, by changing the temperature. I can vary the force, the Casimir force. And when we implement this, basically we can get something like this. So imagine you have this gear, for example, made out of silicon, and you have here this barium titanate crystal, and you're changing the temperature up and down, so varying basically the Casimir force. You get really a Casimir motor. Okay? So we calculated the net torque out of this motor. We are already much further in this design. You can actually do megahertz frequencies in principle with this type of device. Because if you have very small, for example, barium titanate crystal, you can very quickly change the temperature in this crystal. And this is actually, we think, an enabling tool for the nano world. Because if you look at what type of motors actually exist, they're molecular motors, which are a couple of nanometers in size, and then you have MEMS motors, which are maybe 100 micrometers in size. But if you go to the nanoscale machines, that would be the first motor that actually operates in this so-called meso range, so from 100 nanometers to 1 micrometer about. You can design such kind of engines. This is a rotary engine. You can also do linear actuators, whatever. So this is what we are pursuing right now. You can also, calculate for the very first time, actually, the Casimir force on a cantilever. The cantilever is usually used for atomic force microscopes. So with an atomic force microscope, you usually use this to calculate, to measure the Casimir effect. The problem is they use in the equations always the usual Casimir force equation, but here we can really compute what's the effect of the real geometry of the cantilever. And up to now, experiments and the theoretical prediction, they match within a couple of percent, up to 10%. We believe that with this real calculation of the Casimir force, you will get this discrepancy much further below. So, okay, well, I think the physics are quite well understood, and the software really would offer you unique capabilities of really playing real-world Casimir physics, Casimir devices. And we're just about to release our commercial version of that. I have a couple of demo CDs if you would like to play a little bit with the Casimir effect. If you think it's useful, just contact us to get a license. We hope that with the license we can support the further development of this work. Thank you very much. Got the first one. Okay.
Is your power output for your Casimir motor the same as the torque you get out? In other words, power in, power out is equal?
Yeah. I mean, you have to spend energy, right, to heat up the barium titanate crystal. Energy balance, energy is always conserved. Yeah, there is no violation of. I mean, we put in the laws of physics into the simulation, so it cannot break it. But
what's your efficiency then?
The efficiency. We didn't compute specifically the efficiency. The efficiency will really depend on what we can achieve in the manufacturing process. So.
You only showed one activated mechanism. I would assume you could distribute those around the lobes.
True.
To increase your power output.
Yes, actually we have a patent pending for the synchronous Casimir Polder. This is just a concept.
Okay.
But you can actually do megahertz frequencies with this nano engine.
You mentioned you could only have attractive force if you looked at the case of a repulsor.
Yeah, again, there are two ideas in literature for repulsive Casimir forces. One is to use this magnetic polarizability, but there is no material known so far. But you can put anything in the simulation, yeah?
Well, I remember a study presentation where a guy went through this, and he looked at two spheres, and they were repulsive, and a sphere on a plate was repulsive.
That's not, but there are two things known. One is if you play with the magnetic polarizability, And the second one is that if you have two hollow sphere halves, that is predicted, but that's controversial, that these two hollow sphere halves would basically repel. These are the only two credible published ideas literature I know of where people speculate about this. Yeah.
Well, this was at a previous stage, 2002.
Martin, you have the epsilon figure symbol in your temperature modulation. I take it you mean epsilon r and not mu r, correct?
Right.
Are you involved in the studies about possible configuration which have been proposed, able to produce repulsive forces?
No, we're not involved in this type of activity. But the interesting thing is that you can enter specific material parameters. For example, for materials that don't exist right now. Yeah? You can put a hypothetical material inside the software, and you can study how large would be this repulsive force, and you can devise if an experiment is actually possible to measure this amount.
What kind of compatibility does the software have with programs like COMSOL and multiphysics?
You don't need this type of interface. You need two interfaces. One interface, if you would like, is a mesh generator. If you want to go really for details in the gridding, and then you need a post-processor. But you don't need any other physics package. So the post-processing, we're compatible here with two softwares. One is TechPlot, that's a commercial one, it's very widely used, and the other one is OpenDX, that's open source. So with the license of our software and all the open source packages, you have everything you need to operate the software.
Do you foresee this package becoming, I guess, ubiquitous in the nanotech and microelectro machine industry?
We believe that this is an enabling tool for the nano community, actually. So, and with our software, we are not part of Harvard Nano Infrastructure Project, because they also believe that they're running a US-wide nano community project, and they will provide this software actually for the nano community, which is good.
Is the software affordable?
1,000 euros the license. So it's cheaper than many others, but I developed this with my PhD student, and I have somehow to fund my PhD student too. Yeah.
So do you think this could lead to possibly almost enhancing the Casimir effect over the smaller plate? Because I know with aerodynamics, all the equations are for infinitely long wings, but you add a winglet, you get an improvement or performance.
Yeah, you can study, as you've seen with this Casimir engine, that you can study also dynamic applications for this. It's really the first step of doing applications of the Casimir effects. Who knows what we will come up with?
Can you do things like controlling the voltage of the objects that you're simulating? Or?
Controlling the voltage?
Yeah. Just, say you have a situation on a model that you have two different parts that are at a different voltage.
Okay, we didn't include, that's the big advantage actually of the Casimir, for example, engine. The Casimir effect only acts locally, and it doesn't spoil, for example, the electromagnetic environment. If you would in a nano world, just put a few charges, for example, on this gear, you would be immediately stuck with electrostatic influence and all these kind of things. That's actually a big advantage that you separate from electrostatic and electromagnetic forces.
Yesterday, we visited a session discussing robust memories, information memories for space missions, or something like that, whereas a lot of stress due to the automated memory. Can you imagine that you build a Casimir memory that's where mechanically and electrically combination of maybe I don't know what you know what that there is possible to model a memory that can be used for computation?
Look, that's the tool. Our brains are just the imagination. Now we can work on all these things. Yeah, get the license, make a Casimir memory. Whatever we want to do. Yeah? That's the fun part.